Today I have a lot of slides. I'm going to go through them pretty quickly. As you probably know, TTI posts the presentation as well as the video afterwards, so you can go look at them more. But I developed kind of an encyclopedia of stuff, or dictionary of several things. So let me go ahead and get started. I'm going to give credit to a lot of people. There are a lot of presentations, a lot of people I worked with over the years that I took some of their slides, but they also related to some of my own experiences. The main objective we have in pavements, pavement design is developing something durable, and ideally something that wouldn't disintegrate or fail prematurely. And also pavements are resilient, in which I would define as can handle traffic after flooding or icing events. And when I was in Fort Worth, we had to deal with both. And I'll go into a little more detail later on that. In terms of pavement performance, we're looking at structural performance, and that's where we're looking at the thickness design. We're trying to have it withstand a truck traffic loading and environmental effects without premature deterioration or distress. But we also have a functional component, the ride quality, the skid resistance, and also noise reduction, which is obviously important in urban areas such as Fort Worth. We normally design for a specific performance period in these design procedures, like 30-year designs with overlaid intervals of 10 to 15 years. But in general, our pavements have performed for much longer than we've expected. And I can say in Texas, really with the design systems we've used, the only time we've really had premature failures is that we've really blown the traffic estimates, or there may have been some material construction related issue. The topics I'm going to talk about relate both to flexible and rigid pavements. And I'm going to talk about our pavement thickness design procedure and how that's been modified. Asphalt concrete types that relate basically to aggregate gradation. I'm going to focus on the surface mixes mainly, including PFCs and SMAs and the thin overlay mixes. For rigid concrete pavements, we have a new thickness design procedure that I was part of a team on helping develop. I'm going to also talk a little about coefficient of thermal expansion in concrete and why that's important in terms of performance. Well-graded or optimized aggregate gradation, which we use a little bit in Fort Worth, and also some other districts, and also a little discussion on the fine aggregate. Now for pavement structures, this is just a general, this is from David Newcomb. There's several slides from David Newcomb. I'll try to give credit where credit is due. But basically when we're looking at the surface, we're looking at high compression, high stresses, and we want to have a good wearing core, something that can withstand not only the stresses, but also provide adequate skid resistance and ride quality. And usually those are really high quality mixes. Then if you further down, we may use different types of mixes. And I'm going to concentrate a little more on the surface mixes in a little bit. FPS, the Texas Flexible Pavement Design System, has been used in Texas for the last 50 years. It was developed by Frank Scrivener, who is a research engineer at TTI. He worked at AASHTO Road Test in Ottawa, Illinois. And AASHTO Road Test actually measured pavement deflection, or how much the pavement moves under traffic loading. They used the Binkelman beam. And they developed what was called the Surface Curvature Index, which is basically the deflection under the load minus the deflection 12 inches away, and related that to ride quality. Basically, the surface curvature index, the higher it is, the weaker the pavement. Conversely, the lower it is, the more stiff the pavement. And we basically built on that system since the 60s. This is the equation. I just want to say that that's used in FPS. I just want to relate that basically looking at the number 18 KIP equivalents. That's a function of the surface curvature index, the deflection, and also the ride quality, or is also called the present serviceability index, that goes from 0 to 5. There's also a district temperature constant that I think is fixed in the program now. And this is basically another slide showing what we're looking at here in terms of deflection. But the nice thing about that system actually is that it was kind of independent of pavement thickness, and you could actually use it for remaining life calculations. What we're doing now, what TTI has worked with, Fuji has worked quite a bit, it's called TexME. And basically we're still using the FPS, what's now called FPS 21, kind of the original system, where we do a design check on what the system comes up with. We come up with pavement layer thicknesses, but TexME does a design check, and that's where you put in material properties. There, under TTI Project 5798, there are several performance models that you can see here relating to fatigue, cracking, rutting, and so on. And right now the program is being implemented in the department. So it's a direct connection with FPS 21 where it comes up with the pavement layer thicknesses, and then you go do a check to see how it performs on these criteria. So we have specific layer material properties, climatic conditions, traffic obviously, and also variability as inputs. There are several different screens on here, but what is really important about this system is that there's always been discussion, Dr. Nazarian and some others have mentioned this, about trying to tie laboratory testing to actual field performance. Well, we're now getting to that point where we're doing measurements on where you could put in the system properties, lab measure properties such as dynamic modulus, looking at fracture and rutting properties, and so on. You can put that in the system at various temperature levels. You also could put in binder type, gradation, percent RAP, and percent RAS. And so these systems, so you basically, you could put in these material inputs and get some estimate of how well the pavement will perform. Again, the department is doing pilot trials and is a trial implementation and process under this implementation project 6622. We have field test sections in 6 districts, and they have workshops going on right now, as well as a final model verification. There's also a database of flexible pavements that TTI has been collecting. Also, UTEP has assisted in this regard, where we've come up with a Microsoft Access database where we're monitoring the performance of flexible pavements throughout Texas, of various different pavement structures. That can also be used to help calibrate the models in the Texas ME procedure. And there's a lot. You can see here that we have test sections located throughout the state with various different types of pavement structures located. This is an example of what's in there. Basically, we have 115 total, and again, it's various types of pavement layers. Again, looking at different, we have basically 5 climatic types of climatic regions in Texas, which is more than any other state. And again, that describes where we're having, where those are located. We also, you may see these signs in your districts or when you drive through Texas, these blue signs where we have test sections, and we monitor these on a periodic basis. Again, this has been updated since 2010. A lot of material, a lot of data input in here. And again, I'm not going to go through each one of these, but you can see the type of detail we have in this system, what we've been storing in this database. And again, the big core purpose is to monitor how these are actually performing, and we can modify or calibrate our models in our design system to give a better estimate in the future for future pavement designs. We're obviously monitoring rutting and cracking, as well as the present serviceability index and ride quality. And again, you could go when this is all uploaded by TTI, you could look at what all this information in here, but I just want to show you there's an awful lot of information stored that can be very valuable for the department and help us build better pavements. Now, in terms of the concrete pavement type topics, I'm going to talk mainly about the surface layers more than anything. Richard Williams and I have been working together for over 20 years, and our predecessors, Carl Utley and Dave Bass, there's been a lot of stuff we've learned from them too. The first thing I was involved with the department in '88 was in the spec rewrite for all the asphalt items. And one good thing about being in this field is that experience actually means something. Things don't change as much as you think they would. So I'm going to talk about these various courses and some of the experiences I've had and some of the observations we've had. Obviously, the purpose is to choose the right mix for the right application. You're looking at function, ride quality, skid resistance, and noise. Economy, preferably using locally available materials, and obviously performance. You want to have durable layers, rut-resistant bases, and so on. So you're looking constructability, obviously, for all layers, durability for all layers, fatigue resistance and rut resistance, safety, obviously, and noise mitigation. I've shown this slide before. Obviously, we're looking at dense graded, maybe fine at 3 times the nominal maximum aggregate size, and coarse is 4 times. In durability, you're mainly looking for permeability, except for porous friction courses. In some areas of the state, we have to deal with freeze thawing. I'm going to talk about Fort Worth a little bit in that regard a little later. Obviously, we're trying to design where you're not having rutting prematurely. You're designing for certain criteria. As you look at the Hamburg and overlay tests, cycles to cracking or maximum rutting under a number of load cycles. So obviously, we're trying to design against these types of things. I won't go into the binder specification. It's something we've been using since the 1990s in Texas. I'm going to talk a little bit about more there. So you have obviously the 7-day maximum pavement temperature and the minimum pavement temperature involved in the PG specification. Ideal aggregates, it's something that's angular, uniform, gradation with sufficient voids, low porosity and absorption, clean and rough surface texture for skid resistance, and something that hates water. You don't want stripping occurring. So I'll go through this, but basically that's, I forgot to remove that part of it in terms of the, okay. Whoa, I see, excuse me, I'm going up instead of down. Okay, type of mixes, dense graded mixes from type B, C, and D. Stone matrix asphalt, which we use in Fort Worth, and also a permeable friction course. And so the open graded systems are usually the permeable systems, permeable friction course. The well graded, you have good interlock and low permeability. And then you have gap graded, which we used a little bit of, that we had a little problem with. I'll discuss a little bit. These are type of gradations you're looking at for these various surfaces. As you can see, we go from fine dense graded, like a type D or type F, even to a open graded PFC. You can see how the gradation curves change because of that. Dense graded mixes, these are our new workhorse mixes. I can say in Fort Worth, and there's still sections down, Fort Worth used quite a bit since the 70s or 80s, type D as a surface. We did a lot of overlays of concrete pavement using high quality aggregates. At one time we used a lightweight aggregate as a type D on major freeways that were down for over 20 to 25 years and maintained their skid resistance. We got away from that because there was a problem during construction where we just couldn't keep the rollers behind the lay down machine quickly enough. Lightweight aggregate cools down quickly, but they worked very well in our district, and we had high quality materials, and we had basically a recipe mix with AC10 and 3% SBR. And that did work well in our, especially on concrete overlays. Obviously, we're familiar with it. It's low cost. They obviously have the method spec and then a QC/QA spec, and basically use the Texas gyratory, although we use the Superpave gyratory as well. PFCs, this is something that we really started using again when I started in the district back in the late 90s, statewide. Basically uses fibers in the mix, or latex in some cases as well. Odessa and Houston used asphalt rubber PFCs for greater noise reduction, and generally use the higher class aggregate, the surface aggregate class A, which is a high durable skid resistant aggregate. Obviously it's had advantages in terms of draining surface water and reduce splash and spray, which include improved visibility during wet weather and pavement marker visibility. We also increased wet weather friction in most cases because of reduced hydroplaning. In metro areas, people like it because of reduced noise, and we've had some measurements improve quality of runoff water. Asphalt rubber costs more PFC than the regular PFCs, but may be justified in certain instances, especially maintaining noise, a low level of noise. And in Fort Worth, we did the previous generation, what we call plant mix seal, but also porous friction courses. Mainly it started because we had a lot of flush and bleeding seal coats in the district, and actually the district went whole hog with doing it almost throughout the whole district. In terms of noise level, the asphalt rubber PFCs, you can see here, have been considerably lower noise than some of the standard PFCs. And compared to CRCs, there are actually some low noise CRCs I'll discuss in a little bit, but you can see here that asphalt rubber actually showed considerable low noise. And here's some tests from a couple of TTI projects where basically the asphalt rubber over time, this is actually over time, there's a section where it actually did pretty well in keeping its noise properties over time, and it's still quieter than some of the other ones that were measured that tend to start showing some, starting to get noisier over time. That's one concern you do have. They may not necessarily keep their noise reduction properties over time, but the asphalt rubber seemed to do pretty well. In Fort Worth, though, I think this is still the case. We hadn't used PFC since we did that first round of plant mix seals. We did do similar to what was built now with latex and fibers and open gradation. But one thing I learned at the department is they always should listen to your maintenance supervisors. And every time in Fort Worth, we have a considerable number, we may be in a range where we have a considerable number of freeze-thaw cycles and a high enough humidity where every time you saw ice on your windshield, there was a black ice problem on a PFC somewhere. Mark McKendry, Stevensville area engineer, told me about a story. He was driving from Comanche County into Dublin, and he went from a microservicing to a PFC and spun out of control when he hit it. We started hearing more and more of these stories from the maintenance forces, and that was one reason why we got away from it. Even though we thought we got a more durable mix, even on the high volume roadways, we still had this black ice concern. And there's been reports by CTR, TTI, and others that showed that they tend to be this way. And so there was a concern we had to do either not use it or do more frequent de-icing as we got away from it. Functional life has been between the 7 to 10 years for the most part. The other thing I want to discuss, and I found from a maintenance supervisor in Fort Worth, is that he saw when we start building these that the accident rates went down, but then he started seeing an increase in wet weather accidents, high-speed wet weather accidents. And what we surmised is that in some cases, yes, there's a reduced splash and spray, but there's so much of a reduction that people started driving faster and their following distances maybe came closer. So it was kind of encouraged, had this behavior. They don't want to necessarily drive in wet weather, but because the splash and spray had gone, you started seeing these instances. And there was a study in Oslo done about European courses where they didn't see really a change in accident rates. They saw some studies showed there was an increase and some showed there was a decrease. So my caveat is that splash and spray reduction is good, but be aware that in some cases it may encourage people may just drive faster as a result, and they shouldn't be driving faster. That's a caveat. Superpave, this is what we've gotten more into in the department lately. Basically, it has obviously a number of applications. One advantage using Superpave over our workhorse mix is the ability to adjust the binder content by the number of design gyrations. It has more asphalt and it's more crack resistant. It's not prone to rutting. And then what I like the most is SMAs. Although they're very expensive, we've done SMAs in Fort Worth. I remember there was ones we did before I got there in the early 90s that Paul Krugler and Dave Bass designed. Built in the early 90s. By the time I left in 2006, they were still there, and I think they were there for a little longer before they had to reconstruct the roadway for another reason. It could be, obviously, you see it on surface layers on high volume roads. Again, it has fibers and mineral filler as well as possibly SBR latex. It's a gap graded mix with stone on stone contact, high polymer modified binder content, 6% or more. And it's more expensive than this grade asphalt, but we had great experience. In fact, there's a section of 114 that we just built in Wise County back in 2004, and Bill Nelson, who's still here retired, remember that. It's still there 13 years later, and it hasn't changed a bit since we built it. And it's a major aggregate haul route out of Wise County. And so it's more expensive because of what you have to use. It has been, I think, proven to be a durable mix as long as you have a good aggregate on it. In thin bonded friction course, this is placed in I-20 east of 820 and through Arlington recently on a Type D hot mix that was down since 2000. And those look really good too. They're thin lifts as well. I want to talk a little bit about the thin overlay mixes. Obviously, there's been other discussions about this, but they're more expensive, but they're also ultra thin. And as long as you use, I'd say, a surface aggregate class A for the high traffic, and you go through the balanced mix design requirements, you got a good mix. You need to have something good and solid underneath it. But these thin layers, yeah, you don't use wrap or raz in them. You use a surface aggregate, a high surface aggregate class. But they're as long as you have a good surface to build on, they are very durable and they look great. The stripes look great on them too. That's one thing I've noticed. They stayed black. The surfaces stay black, and so you have better contrast with your traffic stripes. And they've been quiet. We recommend surface aggregate class A for the high volume roads and not allowing wrap and raz. Usually the binder content's over 6%. We don't recommend blending. This is actually a slide from Mike Ariano. In Fort Worth, it may be a little better because of the higher quality limestones, but this is from a South Texas source. And when you start doing these blending, and San Antonio did this differential wear course, but you can see here the B's are being crushed while the A's are still fine. So I would say if for high traffic, I'd say stay away from blending and just stay with it aggregate. Basically, you're doing thin mixes, which cost more per ton, but because they're thin, you could pave more. This is another graph in terms of how quiet they are. The thin overlay mixes, we got DBA level of 98. SMAs have been was a little more noisy. Obviously, the seal coats tend to be noisier, but you can see the TOMs have stood out, and asphalt rubber as well has stood out in terms of their noise. And my feeling is that the TOMs have probably better noise reduction properties. They probably keep their noise reduction properties over time a little better. Now, that's all for asphalt, but let me talk about concrete a little bit. And I had 8 minutes left, so I'm counting. Anyway, there have been a variety of projects over the past 20 years that TxDOT has sponsored relating to concrete pavement. And the main, and I'm not going to go through all these, but we're looking a lot focused on aggregate sources. We had problems with the silicious gravels in particular, the problem with CRC that I'll talk about a little bit. But we've been doing a lot of research over the years, and it's actually kind of culminated in a new design procedure for CRCP. CRCP is continuously reinforced concrete pavement. There are only joints at bridge ends and where it stops at end of day's paving. We expect it to crack at a certain crack spacing, usually 3 to 10 feet, and those cracks are kept closed by steel. And we developed, there was a project that Texas Tech had led, but TTI participated in. I was on the project. Dr. Moon Wan led it, where he came up with a new design procedure that replaced the procedure that they were using from the old AASHTO procedure. It's a pretty simple procedure. We designed for 30 years in terms of the traffic. 10 punch outs per mile, that's the main failure mode that we're concerned about with CRCP. So we're looking, in this new procedure, we put into thickness and just basically see what, with the traffic level and so on, see what would work. So 10 punch outs per mile is usually recommended. You may want to go down if you're in interstate to use 8 or so punch outs per mile. You put in your design traffic, total number of lanes, the trial slab thickness, the modulus of rupture. The concrete elastic modulus and coefficient of thermal expansion are fixed in it. We also have support layer information. It's really important with concrete to have a good support, and those values are put in the system as well. It's all in a worksheet. And again, we're designing against this type of failure, what we call a punch out. We first thought that most of these were full depth punch outs, but now we're finding from what I observed, when Jimmy Bodiford, the Weatherford engineer, observed in 2000, and then Moon had observed, that a lot of these failures are actually happening where it's actually cracking at the level of the steel, the horizontal lamination. Our design approach, we're still doing a lot that's prescriptive for rigid pavement design, a 6-inch cement treated base, a 1-inch bond breaker, or a 4-inch ACP or asphalt stabilized base. We've been doing this since the 60s or 70s and found that's the best way to really build these. We've had many bad experiences built on flexible base and on soil and so on where the concrete starts failing prematurely. The main thing for CRCP, we measure coefficient of thermal expansion, basically looking how much expands and contracts due to temperature. Right now for CRCP, it's required that the coefficient of thermal expansion be below 5.5. And also we give credit to using actually lower steel if the coefficient of thermal expansion is below 4. Now why we're using this as a criteria? Well, I'll go to that a little bit, but basically we're looking at, also we look at fine aggregate where we're using silicious fines. The problem with coat, we found with the higher coat or coefficient related to stress in CRCP is this type of spalling. This is what we saw a lot in Houston, but I saw it in Fort Worth as well with some gravels we'd used. Where you got a surface spalling, you ended up having to repair all these cracks, and you have every 3 to 8 feet to repair them. It's a lot of repair. It's using, basically, we found the relationship between spalling and the coat, and so we've done a lot of research, but we basically said, for CRCP, we haven't found anything where you could use a high coat aggregate in CRCP. So that's why it's in the spec, about 5.5 or below. We have shallow spalling at transverse cracks, and the same type of thing. The other thing we found for some of these higher coat aggregates, we start having what we call this horizontal cracking that leads to this type of punch-out failure that I saw before. It starts at the crack, at the transverse crack, which goes full depth. We have these occurring at the steel level, and we don't want to have that. Otherwise, we start having premature failures and punch-outs. And here's another photo of it as well. We're having it split, essentially, where the steel's located. However, we've built, though, there's about 4,000, 5,000 lane miles of CPCD. As long as you don't use dowels and you have a good base underneath it, we found excellent performance. Dallas District has built a lot of it this way, and some of it's still been just really, really good. But you really have to, in some ways, have to be even more concerned about base support underneath it. Having a stabilized base underneath it, also handling your subgrade underneath it as swelling soil, doing enough treatment or even replacement in order to be sure you have a good performing pavement. So none of the distresses previously mentioned with CRCP have been found using high coat aggregates and jointed. And the 15-foot joint spacing has seemed to work out real well. And so TxDOT allows any coarse aggregate to be used and jointed. Now finally, To talk about optimized aggregation, Fort Worth did Ralph Brown kind of pioneered this in the Fort Worth district. El Paso had used this as well. Basically, we're looking at a well-graded, optimized aggregation is another way of saying having a well-graded concrete. And the idea is that you could still get the same strength using lower cement contents or paste contents and with more aggregate, more durable aggregate. This is the Shieldstone curve, but basically one concern obviously when you start using these well-graded materials in concrete, that's still workable. You get it behind a slip form paver and you still get a good surface. We increase the performance of these optimized aggregate gradation by relying more on the aggregate strength. You enhance concrete workability, and you minimize shrinkage cracking, which is a killer in terms of looking at durability. And you save money by reducing the amount of paste in the mix. And in terms of shrinkage versus normal concrete, the paste itself is obviously what's causing the shrinkage. That's the cement and the fine aggregate. But when you start looking at optimized graded concrete, you definitely minimize shrinkage. This is from the 1938 project in Fort Worth. We looked at a standard mix versus an optimized gradation mix. Reduced the sack content by 1 sack per cubic yard and got an increase in compressive strength. And so it's something that I know we've used in some districts. I think one people have concern with is that it looks really rocky when you put it in front of the slip form paver. But in 1938, I have a picture of that, but afterwards actually the paste comes in really nicely and get a smooth surface. These are 2 cores I have. This is a gap graded on the left where you can see a lot more paste. This well graded on the right is from I-35 between Burleson and I-20 in Tarrant County. That was done in the mid-70s. And this was a well graded mix. This is where they're still using intermediate aggregate. That's still the surface today in Fort Worth. And they did do a diamond grinding job on it, but it was definitely a really good performing mix. Again, when you look at these mixes, they look really rocky. You can see how the paste, someone put their foot on it so you can see the paste come up. And we look at it, had a slip form paver. I remember when I was out here on the job, it did scare some people. I said, can we even finish that? But right behind the paver, it was really smooth. The paste came in nicely. But I think some people were scared of it because it just looked so rocky when you put ahead of it. Then fine aggregate, that really provides a skid resistance for concrete pavement. An acid and soluble requirement for fine aggregate helps ensure adequate skid resistance. That's why we're using basically silicious fines to this day, along with the surface texture. And finally, to talk a little about CRCs. Again, you could get some quiet CRCs. There was one that was about 100 that used a decent type of surface texture. You know, we've seen some, obviously, if it's CRC, if it's tined versus untined. But if you get into these next generation concrete surfaces that you can look up, ACPA has had some guidelines, Texas Concrete Pavement Association has worked with it. With this next generation surface, some that are basically longitudinal tines along with some other diamond grinding, we're getting down to 99 dBA versus 106 dBA for some other tining, so that worked very well. Again, let me give credit to all these people that provided slides for this, slides I got for other presentations, but again, this will be posted on the website so you can look at it more and look at these other studies if you have more interest in it. And that concludes my presentation. Everyone must go drink now. Yes, sir. Beg your pardon? Yeah, that's right. If you go to the TxDOT website, you can actually search for CRCP ME. TxDOT website, you can actually download the spreadsheet from the website. I think there's some work. They're asking is there going to be another design procedure for CPCD. I think there's a research project that started on that.